All right, hello everyone. Welcome to the Future of CIP Optimization webinar. Just before we get started, I would just like to kindly ask you, if you can hear me, just go to the panel on the right side of your screen and write in the chat or in the question area if you're able to hear me well, please, so we can move forward.
I see one person says they can hear us.
Yeah, everyone can hear us. Awesome. Thank you, guys. Thank you, everyone, for that one. Good. So before we get started, I know after COVID and everything else, I'm pretty sure most of you are familiar with the GoToWebinar. But just a quick reminder, on the right side of your screen, you can download the presentation, and you can also type in all your questions and comments during the presentation. By the end of the presentation, we're going to have a couple of minutes to answer some of them. If your question is not answered today, we'll come back to you later on, so you don't have to worry about it. And this session is also being recorded, so you'll be able to, let's say, watch it again in case you missed anything. Okay. Moving forward, so I'm going to introduce myself and the other presenters. My name is Gustavo Queiroz. I'm the industry manager responsible for the food and beverage market here in Australia. And I've been working with Endress+Hauser for more than 10 years right now. And I'm going to hand it over to Dhiren to introduce himself. Dhiren?
So hi, I'm Dhiren. I'm also the industry manager for food and beverage, but I'm based in a different continent. I'm based in South Africa. And I've also been with Endress+Hauser now for over 10 years. So I'll hand over to our colleague in Germany, Aliu. Just introduce yourself.
I'm Aliu Steven-Kafo. I'm the innovation manager based in the production center at Endress+Hauser Level and Pressure in Germany. And I'm directly responsible for this product.
Excellent, excellent. Thank you very much, Aliu. Thank you, Dhiren. So I think we can start our conversation. We can start our chat. And Dhiren, I'm going to ask you a question. I think this will be the start of the presentation. What are the different types of cleaning techniques in the food and beverage industry?
So when it comes to cleaning in the food and beverage industry, you know, I've come across three sort of cleaning methodologies that a lot of our food customers typically use. The one which is very mechanically intensive, which means removing piping from the process and basically putting it into a bath of a solution, chemical solution, and cleaning it this way. And as I mentioned, you know, it is time consuming. I don't see it a lot these days, but one or two sites you do get it, especially in the meat industry. They typically would use this sort of methodology. The most common practice that I've noticed is the CIP. So this is cleaning in place, whereby there's no mechanical activity done in terms of removing piping from the line. Basically, the process is cleaned using chemicals. So normally this is done with a rinsing of the line, then an alkali solution is pumped through the process for a period of time. It's then rinsed again, and then the line is considered to be clean. Normally these comes in typical skid fashions from skid builders, so quite a compact automated unit. And then you also get the sterilization, not common practice in food plants, mostly in life science industry. I would think of it, pharmaceutical applications, whereby similar to CIP, you know, they clean the line with water, they run CIP, they then clean the line with water again, and then they sterilize it with steam. Obviously, this is utilizing a lot of energy due to the fact that you have to run steam through the lines. So, yeah, these are typically the three methodologies that we use.
Excellent. So going a little bit deeper into that question, what are the factors that really, let's say, affect the efficiency of a cleaning?
So in terms of the factors, we typically base this off the Sinner cycle. So you can see in the presentation here, CIPing is based basically on four four aspects. The one being temperature. Temperature is key. Obviously, if you don't have the right amount of temperature in your line to clean, especially with the hot water and the CIP, what happens is you don't kill off the bacteria. If it's too high, you're actually wasting energy in that case. So typically, rule of thumb is no less than 60 degrees and no higher than 90 degrees. This is to attain optimal temperature of the process. The next one that we have is time. So time, the physical time it takes for the activity. So a lot of these processes are based on a recipe, and the rule of thumb is normally you run your CIP for around 45 minutes. This typically, I haven't come across a plant that's changed this. It's always, no matter whether the plant was cleaned or the cleaning activity was completed after 42 minutes, a process plant will always clean for 45 minutes. You also then have the chemical activity, so the physical chemical that you use, and a lot of plants, they use various chemicals, but the most common chemical that they use is sodium hydroxide, which is NaOH, and this is normally used called caustic on site. So they use a caustic solution to clean. Obviously, the concentration of the caustic is critical. If you have a low concentration, you're not cleaning actively, but if you have a high concentration, you're actually wasting chemical, as an example. And then finally, you obviously have the physical action of cleaning. So you need to achieve a certain flow rate in order to create a turbulent flow. If you have quite a laminar stable flow, you're not agitating the line enough to try and get into the crevices to physically clean the line. So this is why typically we say a minimum of 1.5 meters per second in terms of flow velocity to create that turbulent agitation in terms of the flow. So this is basically, the Sinner cycle in a whole in terms of the cleaning process. Gustavo, what does the control of a CIP system typically look like?
Excellent. Thank you very much, Dhiren. This is a really good question. I have here a basic diagram on how a CIP process works. So in summary, you have to dose your chemicals to a dilute solution, usually around 1 to 2.5%. You have to heat it, and then you send this heated chemical solution into your pipes within a controlled velocity, as already mentioned, to clean all the pipes, vessels, tanks, and then you monitor the return of your CIP, and you use instrumentation to monitor and control all these stages but one. So as you already mentioned, we have four, let's say, key factors that really affect the efficiency of our cleaning. We usually control three of them: the chemical action, the temperature action, and the mechanical action. But in general, throughout all the food and beverage industries that I had experience or I had the pleasure to meet, none of them have a CIP controlled with a time, with a control based on time. All their times are fixed. So we have instrumentation to monitor and control these three variables, and we also have some side instrumentation to control, especially for safety control on for the tanks and for the pumps as well. Before we move on to the rest of the presentation, before we continue to the presentation, I'm gonna ask you guys to answer a quick poll. So the first question is, what are the most critical parameters in your CIP cycle? Okay, I'm gonna launch the poll right now, and I'm gonna give you around 10 to 15 seconds. There you go, launch. And I want you guys to give us an honest, let's say, answer on what are the variables that you control and that you really consider that are really critical for your process. Okay, I'm pretty sure you guys already have. All right, so conductivity, flow, temperature, time. Okay, it's changing a little bit. 89% conductivity, yeah, so we have a tie. Oh, that's really good. Well, as you already mentioned, Dhiren, it seems like flow, temperature, time, and conductivity / concentration are well known across the food and beverage industry. We can see that turbidity and color are not well, let's say, explored. That's really good because we're going to cover this topic and how we can optimize your process with turbidity and color sensors as well. Thank you very much for those of you who voted. I'm going to close this one so we can continue our presentation. Cool. So let's get started with the first, let's say, parameter that we need to monitor and control in a CIP process, which is conductivity. Conductivity has two main, let's say, roles within a CIP process. The first one is for phase separation. So you can use a conductivity sensor to identify whether you have water or whether you have, let's say, cleaning solution. Whenever you add, let's say, an acid, a base, or salt into water, we have a tendency to increase the conductivity, and a conductivity sensor can monitor and control this really, really well. And we also use the conductivity sensor to dose chemicals as well. So whenever you usually have concentrated IBC tanks, and you dose from these concentrated IBC tanks into the concentration that you need for a proper cleaning. And we have a very interesting, if you look at the chart at the bottom left of the presentation, we have a very interesting relationship between the conductivity and the concentration of chemicals in general. So this is a well-known and established parameter within the food and beverage industry. But what we do often neglect is the accuracy of the sensors we use for our CIP process, especially for chemical dosing. As you can see in this slide here, if we use these are the numbers we got from a real customer. If you use 600,000 of hydrogen sodium hydroxide a year, if you have a conductivity sensor with an accuracy of 2% of the measuring range, this can lead you, let's say, to an overdose of nearly 1,200 kilograms of NaOH, or sodium hydroxide. Whether if you have a very high accurate conductivity sensor, for example, you have a sensor with a 0.5% accuracy, this uncertainty or this overdosage, depending on the accuracy, based on the uncertainty, can be reduced to 60 kilograms per liter. So as a first step for CIP optimization, if you really want to reduce chemicals, if you really want to, let's say, try to approach, try to find a way on how to improve your CIP, this is the easiest and fastest, say, step for you to improve your chemical dosing. All right. Moving to the second topic, so using as a hook the poll you guys just answered, another very interesting and important measurement we can use if you really want to reduce water and really want to improve your your product recovery is to use an optical sensor, whether a turbidity or a color sensor, at the return of your CIP process. So every time you finish a batch, you often have some residual products within pipes and tanks, and you have to push it to your, let's say, to your stored tanks or send it to drain. This kind of control is usually based on two different approaches. You can either have, let's say, a time-controlled approach where you can, let's say, push it for a while, for a period of time, and then send all the rest to the drain. You can have a really good potential for product loss and water loss in this approach. And the second approach is by using like an operator to go and check like a side glass and see whether when you have the change from water to product or product to water, which is also sometimes not efficient because the operator can be distracted or can be focused on any other task. So keep this in mind whenever you have the, let's say, a sensor or a solution that can identify the transitions between products in a very fast way, and you can create an automation behind it. You have a really good potential for savings. But this is not the only potential for savings. You can also save. You can also have a really good potential for savings with temperature sensors. And I'm going to ask you, Darren, can you explore a little bit more on how our customers can save money with temperature sensors?
Sure. So as you saw in the cycle, a lot of the cleaning is based on temperature, and temperature is only considered to be a consumable product. Very neglected, very not well maintained. And let's face it, temperature is critical in every single process in the food and beverage industry. As I mentioned, you want to achieve between 60 and 90-degree temperature to ensure effective cleaning in your process. So this is why fast, reliable, and accurate temperature measurement is really important. So we have actually a variety of sensors that potentially could use. You get the very basic TM311, as you can see there. This is very simple, very basic, easy plug and play sort of device. Then you typically get your TM401 sensor as well. That can also have a quick sense. So what this means is that the sensor actually responds a lot quicker than your traditional RTD temperature. And how we managed to achieve this was we actually mounted the physical sensor not in the stem, as you want to call it, but directly on the tip of the temperature probe, thus allowing us to be as quick response as possible. And with regards to our response time, we typically between 6 to 8 times quicker in response than your typical PT100 that you use. The next one is, our quick neck. So if you look at the temperature probe, the third temperature probe that you see there, this is actually quite a unique design that we have, whereby you can use just half a turn and you are able to remove the sensor from the process. So you might be asking me, okay, how does removing the sensor from the process help optimize my my cleaning? Well, as I mentioned, temperature is not a very well maintained measurement point due to the fact that it takes a long time to calibrate a temperature probe. With the quick neck, this enables you to remove the sensor a lot quicker with very little mechanical action. You don't need to remove the terminals, disconnect the probe. You literally half a turn, you're able to remove it and put it in your test bath, and maintain it. But talking about maintaining temperature, this can be quite a cumbersome exercise in terms of time, because to maintain a temperature can take between, depending on how many calibration points you're going to use, between 30 to 45 minutes, maybe sometimes an hour, hour and a half, depending on how many calibration points. So actually, Endress+Hauser came up with a new type of sensor. This took 10 years of research and development, which is our TrustSense sensor. This is the world's first and currently only on the marketplace self-calibrating temperature transmitter, and it's able to calibrate itself at 118 degrees. But you might be saying, Dhiren, you're beating around the bush here, because you just told us that CIP process only measures between 60 to 90 degrees, and now you're talking about a calibration probe that only measures at 100 or calibrates itself at 118 degrees. Well, the reason I mention it to you is a traditional temperature calibration can vary between 3 to 5 points, that you have to calibrate. With this probe, on the other hand, you only need to calibrate 1 point, and it's able to adjust itself and calibrate itself to that 118 degree point. And this is why it can benefit in terms of reducing your maintenance activity. So temperature is not only an important measurement, there's also flow and level as well. That is also critical in terms of measuring on site. So when it comes to flow, as I mentioned, flow creates the mechanical activity. So if you have too low a flow, you're not getting enough cleaning occurring. So you need, as I mentioned, 1.5 meters per second flow rate in order to create that agitation activity to clean all the crevices, all the T-joints, etc. So that's why flow is also an important measurement. And for instance, we have our H100, which is a very economical flow meter that works very well in this this sort of environment and application. You also, Gustavo mentioned in terms of these IBC containers. So I don't know if you guys seen on your site, you have these little plastic 1,000-liter IBC containers. They're known as intermediate bulk containers. So a lot of sites have these. They normally provided by external chemical suppliers. But what a lot of customers neglect to do is actually measure the level in them. And this can become quite a problem, especially when you're running low on your concentrated caustic and you need to clean your process. Now you don't have the right quantity of caustic in your process to actually clean it effectively. So what we actually came up with is quite a compact, robust radar device. If you can see on the top, this device is a completely plug and play device. It has a little battery pack inside. It communicates to the cloud. You're able to bring that information back into your system to actually monitor your concentrate, as an example. Also level measurements. So you have a lot of tanks on your site, your CIP tank, your hot water tank, your recovery tank. You need to measure the level. And typically we use the go-to is a pressure transmitter, hydrostatic pressure that measures level, as well as you can potentially use a capacitance sensor as well for this. One neglected parameter that what I see quite often is the level switches, because it doesn't directly impact on the measurement, but it does impact on safety. So not so much the low level switch, although they can play a part in your inventory monitoring of how much of product you have if it's too low, in your tank. But certainly the high level is quite critical in terms of safety, for the fact that you're dealing with caustic. This is an alkali solution. If it does come in contact with an individual's eyes, hands, it is quite a corrosive substance, and it can cause bodily harm to an individual. So especially if you want to protect your colleagues or your staff on site, this is typically a very economical solution, our FTL51H, that you can install as a high level switch, just as a safety, so you don't overfill the tank. So in terms of these are just some of the installations or the instruments that we can use to measure in a CIP process. But in terms of the current practices, time is the main factor. At the end of the day, time dictates everything when it comes to CIP. As I mentioned, a lot of plants use the 45-minute principle, whereby they only clean for 45 minutes. Or the recommendation is to clean for 45 minutes, even though the tank could have been cleaned earlier, but we always use the 45 minutes. And let's face it, plant cleaning is downtime. The only time that's not considered downtime is production. And plant cleaning, it takes a lot of time. It takes a lot of energy as well, and how effective is your plant cleaning? So, the recommendation is always you clean after production, but sometimes this is not the case. So Gustavo, do you have an example of a client or a customer that we've seen whereby they've done cleaning, but it wasn't actually done correctly?
Yes, I do. That's a really good point, Darren. Thank you for the great explanation. Yeah, I have a really interesting photo here that I'm sharing with you. Well, in the food and beverage industry, as in any other type of industry, we can have different types of soiling, and each type of soiling has a very, let's say, specific challenge. And what we do know is the soiling conditions is time dependent, and it's also process dependent. So if the soiling is exposed to high temperature, it will get into a condition that will be harder to clean. Still, most of the customers, the majority of them still use, let's say, a time constant approach for the cleaning. Okay. So here we have an example of a tank. If you judge by the bottom of the tank, by the lower area of the tank, you can see the sensor, the tank is clean. But if you look at the upper area, even though you have here it's a spray jet, you can also see that there is some soiling at the top area of the sensor. So here comes another question for you, Darren. If a customer has a situation like this, or for cleaning in general, what are the general way, what are the alternatives the customers have to check if their CIP is well performed and is really efficient?
Well, the first one is always a visual inspection. So a lot of customers will physically go and inspect the tank. But if you follow hygienic processes, that's not actually the right way to do it, because the moment you open up the top of the tank, you're allowing contaminants inside the tank. Thereby the tank becomes, it needs to be cleaned again. So although it's the most effective way at the moment, currently is a visual inspection where you open up the hatch and inspect inside, it's not actually the right way to do it. The other one is whereby a lab tech comes and does a swab in the line, and then they take that swab and they go and get it analyzed. This is also a very time-consuming analysis, depending on the load in the lab. Normally, you only have 2 or 3 lab technicians, and they're doing a lot of sampling around the plant, depending on the size of the plant. So this can be a very long exercise. So remember, I mentioned the 45-minute. It's not actually 45 minutes. It's more like maybe 2 to 3 hours that you're actually cleaning your plant. In terms of the cycle and the checking and the approvals before you can actually create or start your next batch. You also have the pH measurement. You have the conductivity measurement that verifies whether the concentration that you use was correct. Also the temperature, whether you actually reach the temperature. But then again, temperature can also be depending on your maintenance. A lot of customers only maintain temperature once a year. So I'm just using an example here, but what if in 6 months your temperature calibration goes out and your temperature starts to drift? Maybe you're not achieving that 60 degrees, you're only achieving that 55 degrees. There's a lot of factors that play that don't allow us to achieve 100% accurate validation of CIP measurement in the process. And this is why CIPing is critical and important, and also the way to measure how effective a CIP has been conducted is really important. Besides the CIP, the water, the chemicals, depending on the maintenance of the equipment that you use, if you're relying on that and you're not maintaining the equipment, you can't really validate whether your CIP has been done correctly. So that poses my next question to you, Gustavo. Is there an instrument in the marketplace that can actually measure how effective our CIP has been done in the process?
Awesome. Great question, Darren. So I'm going to talk a little bit more about the QMW43, which is a new sensor Endress+Hauser developed and launched, which is a sensor that can measure the build-up height within tanks and pipes, which is a very interesting approach. You can see on the slide, this is a very interesting sensor. We can have, the conventional hygienic process connections. We also have flush installations, because we really want the sensor to mimic or to copy the same condition as pipes and tanks. And based on the conductivity, the sensor is able to measure conductivity and capacitance. And based on the capacitance, we are able to determine the build-up height. So this is a very interesting approach, especially if you want to check, if you want to validate whether a specific point is cleaned or not, or if you want to set up your CIP to clean your process based on the build-up level. So I'm going to ask Alu. Alu prepared a demonstration video showing how the QMW43 actually works. And I'm going to ask Alu to come and, hey Alu, are you there?
Yes, I'm right here.
Hey, Alu, thank you very much. So I'm going to give play so you can explain a little bit more in details what's going on with the QMW43 here, okay?
Okay. So guys, basically as indicated by Gustavo, that the device actually measures the build-up height and conductivity of different media. So, and which is useful in CIP optimization, phase separation, and also, as we said, in the blending applications in the food and beverage industry. So basically what is happening here is we are simulating the build-up height and conductivity measurements by applying a thin film of the measurement media on the sensor surface. Just look at the mobile phone. It displays both the conductivity as well as the build-up height. Take a look at the build-up height. We are getting 2.1. And now we are adding some more media onto the sensor surface. And take a look. Now look at the resulting readings on build-up height and conductivity. You've seen that the build-up height has actually increased to 4.6, which shows that it's actually increasing as the production continues. So this is what happens, but this is like on a desktop measurement. There are 2 other videos that will be screened that actually shows what happens exactly in the production phase. So please play the first video. So in the first video, what happens is during production, you do expect to have fouling on the installation surface. So if you look at the sensor, which is being zoomed out, you will see that you have some buildup of a sticky media covering or partially covering the sensor surface, which can be seen also from the display readings. You can see the conductivity is above 300 and the buildup height has actually reduced to 3.9. On the next video, which will be screened, which in that video will actually try to like do a CIP or a cleaning process. And the essence of cleaning is actually to remove whatever buildup that is on the installation wall. So when that is successful, we expect to see that the buildup height value that we are getting 3.6 to actually change to what is expected when in a clean installation underwater, which should actually be 7.5. So please, next video, please. So in the next video, as I indicated, basically we are mimicking the CIP process. So in here, CIP has been done, and the sensor, as you can see, is now totally clean. The buildup height, as you can see, being displayed is 9.5. So that is indicative of the fact that the installation has been clean, as determined by the liquid train QMW43. So basically, this is how this device actually helps in optimizing your cleaning process, and also it can be used also for phase separation, because then you can use the conductivity output variable to actually determine one media from another, and also for blending applications. Over
Excellent. Thank you very much, Alun. Just one question. That's something that came up during the previous presentation as well. What is the minimum build-up height the QMW43 is able to detect?
The minimum. Well, actually, yeah. the configuration starts from 0, which is the minimum, to 10. That is how it's actually graduated. So if the installation is totally clean in an empty state, because then we are talking about 2 different states. We have the empty state as well as the clean, the full state. So if you have an empty state that is totally clean, what you expect to see as the buildup height should be 0 millimeters. And then it can actually proceed, it can actually go up to 10 maximum.
Excellent. Thank you. Thank you very much. What is the minimum resolution for the QMW43?
Well, in terms of the build-up heights, of course, yes. The thing is, well, in terms of the build-up heights, basically it starts reading from 0.1, which is like, yeah, a slight tweak, because then if it is displaying 0.1, it therefore means that the build-up that is on the sensor surface is actually 0.1 or below. That is like, yeah, because it doesn't actually show values below 0.1. For instance, let's say if you have a build-up height on the sensor surface, which is like 0.05, it does not really show because it actually reads to 1 decimal place. So, excellent. Yeah.
Thank you very much, Alun. Really good. So we have a couple of applications and signal interpretations we want to share with you. So just to give you a quick summary on how the QMW43 works. So it's a build-up and conductivity sensor. So we are able to measure the build-up in tanks, pipes, but also we can use it to optimize blending processes. So whenever you have 2, let's say, different components being mixed together, you can use both the capacitance and the conductivity measurement to make sure that your product is really well mixed, which is a really interesting application for this sensor in a specific. Now I'm going to ask Diren. Diren, what are the possible, let's say, installation points we have for the QMW43?
Diren, you need to unmute yourself.
I can hear me now. Good.
Yeah,
so basically, as Gustavo, you showed in the previous slides, you have a tank with a spray ball valve. you know, and cleaning normally will occur naturally on the side of the walls and the base of the tank. But it does occur that, you know, the level in the tank does increase above the spray bowl, and product does collect above it. So an ideal solution would be to install the QMW 43 above the spray bowl valve as an indication if the entire tank has been cleaned. Another would be on corners and bends. So if you see in this example where the truck is, you wouldn't install the build-up sensor on a straight line, because this naturally is where cleaning does occur. Where cleaning doesn't naturally occur is on corners and bends, you know, because the welding is slightly different over here. You get pivoting or pitting in the welding, so microorganisms can build up over here. So this is where you'd want to measure as well. Also, heat exchangers. Obviously, as you know, heat exchanger plates are quite narrow and small, so we can't really install it in the heat exchanger or on the heat exchanger plates. But what is a good indication is to measure the buildup on the inlet and the outlet, and measure the differential between those buildups, and that indicates very nicely to us whether we have buildup in our heat exchanger, as an example. Also at the bottom of the tanks, on the side of the walls, as I mentioned. So yeah, these are various places. Also, it can be used. The use cases where we've done it before is in CIP and cleaning optimization, to measure the build-up height for heating optimization, scaling recognition, product recognition, as well as blending optimization. And you might say, oh, product recognition, how do we do that? Well, as my colleagues mentioned before, we don't only measure build-up height, we also measure conductivity. So this can also be a nice effective way to recognize what product you have in the tank by utilizing the conductivity of the sensor as well. And these are basically some of the you know, use cases that we've done. We've done demonstrations before with customers, whereby we've used these devices. I do get some feedback. Is something unmuted? I'm not too sure. I think everybody is muted, right?
Yeah, everyone's muted. I'm gonna mute myself here.
No problem. So with regards to some trials that we've done, and we do offer trials because, let's face it, this is a new concept. It's a new parameter that you want to call it, that we're measuring build-up analysis. So an application where we've done is the hot water application. So for those that are not familiar, this is in a brewery whereby you have wort from a wort kettle, and this wort typically causes a lot of fouling. As you can see in this the picture with the pipe, there is some sort of fouling that occurs over here, and you actually want to clean it so that you don't have this fouling, because you can cross-contaminate different batches of your brew, as an example. And this is a very nice example where we've done it. And in the next slide, you'll see the actual trend of what we've done, and we trended our results. So you know, the trend has occurred over a period of time. You can see here, we did, this trend was 4 cycles. And what you can see over here, you see at the bottom, we trended some various parameters, but we trended the buildup. So you can see with the CIP, the product, as we ran production, the buildup started to increase. We CIP'd. At this point of CIP that occurred, we brought the buildup height lower. And by doing that CIP, we were able to actually reduce the amount of buildup occurring in the tank, thus increasing the amount of production that occurs in this tank. So you can see in this instance here, we increased the frequency to result in a decrease in the buildup height for this hot water application. The vice versa can occur as well, whereby we actually reduce the amount of CIP time and increase the production. But this all depends on the type of application that we install it in. Whether it's a heat exchanger, hot water application, etc. And as you can see over here in the next example, we have a calculation that we worked out. You know, in terms of customer saving, just 5 minutes of cleaning, and just ignore the fact that you also have to do the laboratory test, the validation, etc., etc. Just 5 minutes of saving on your cleaning water cycle in a DN200 pipe around 1 meters per second, you know, you save around call it 10 cubes of water. If the water costs around 4 euros a cube, that equates to, especially if you have CIP every week, around 2,080 euros per year. With that, you know, you also gain in production time, because you're reducing your CIP time, thus increasing your production time. And as I mentioned, by increasing your production time, that's also the lab time as well, which is like 45 minutes to an hour. You gain around 10 cubes of wort production a week. This is around 400 meter cubed of beer a year, which equates to around 784,000 euros per year. So you're not only saving on water, you're also gaining on production. And let's face it, in this day and age with COVID hitting us, everybody is focused on increasing the amount of production that they can output. So as I mentioned earlier, cleaning is considered downtime. If we can increase it by 5 minutes, this is the savings that you make, and also you're increasing on your production. So this is just some examples that I've used. Gustavo, do you have other examples or applications that we can use the QMW43 in?
Sorry, I was muted. We do have several other applications, and as we approached, this is a build-up sensor, so we can always discover new applications. We are really keen to go for trials and hear our customer needs. We have a couple of applications here that represents a really good potential for the QMW43. The first one for bottle washer. We have a very, let's say, visible scale formation in the final rings compartment, and you can use the QMW43 to help you optimize periodic descaling, to help you optimize the detergents that you use, and to determine what is the right frequency of rings with water of a bottle washer. Okay. Some other application, tunnel pasteurizer, especially to identify fouling, scaling, and corrosion. This is something that is really interesting for application for the QMW43, and you can use these measurements to optimize your cleaning intervals. And another really good application, as we already covered, trying to find really what are the fouling, the build-up height, and really to identify what, let's say, really hard to clean areas and points in your process in general to really, help you identify and determine what is the right routine for you to ensure the maximum efficiency cleaning. Okay, so just give you guys a summary on the QMW43. What are, let's say, what is the really value add for you? We can help you guys ensure your product safety. As we mentioned, instead of using a time-based approach, which if something changes in your process, you cannot ensure the efficiency of your cleaning. With an online measurement, you can ensure that you have zero scale, you have zero buildup on that specific point. So this really can avoid this, help you improve and reduce any kind of microbiological contamination. We help you improve your product quality, especially with mixing applications, so you can ensure that every batch comes exactly with the same consistency. And the third one, which I think is really the highlight over the QMW43, is to increase your plant availability. Instead of, let's say, spending time with very intensive manual inspections, if you have an online measurement that is really reliable and can really reduce the time for you to start your process as soon as possible, this is a really good, let's say, gain in productivity increase for you. Okay, we're getting to the end of the presentation, to the end of our chat. We do have one more poll here that we would be really happy to you guys to answer. And the question now is, what are the main challenges on adopting a new technology for CIP optimization? So I'm gonna pop this one for you. It should be live by now. So we have 5 different, let's say, options. From your experience for your industry in specific, what are the main challenges, let's say, for you to choose a new technology to improve your CIP process? I can see that some of them are already coming. Reliability is the top one. Mechanical installation is coming second. Oh, mechanical installation just took the top position. We have reliability, proof of concept as second. Changes in SOP is not coming, and yeah, no challenges so far. It's not an option. Okay, 48% of the people already voted. I'm gonna give you guys a couple more seconds, and then we can close this one. Any comments from your side, Darren?
Yeah, so obviously we can see here mechanical installation is number one, and proof of concept is number two. 31% of you say, it's a proof of concept. Obviously, this is a new measurement technology, and you're going to be relying on it for the cleanliness and efficacy of your cleaning cycles, whether your process is clean or not. So with regards to coming to proof of concept, we've trialed this at various sites, and we open to trialing these devices. So yeah, get in touch with one of us if you want to prove this sort of measurement in your process to increase your productivity and your cleanliness on site. Yeah, get a hold of either myself or Gustavo if you're based in Australia to try out a unit from us.
Excellent, excellent. Thank you very much, Darren. All right, so these bring us to the conclusion of our webinar today. Just some of the highlights that we would really like to mention with you. So the use of a hygienic design is really a must for you to ensure the food safety and really reduce your costs. So all E&H instrumentation has EHEDG and 3A certification. So everything that we're talking about today, they can all can be installed in your process. They can all be clean, and we can ensure that your CIP process will remove any kind of buildup, any kind of dirt, and the sensor will completely cleaned after your CIP. Some of the highlights, especially on the 3 ways to optimize your CIP, the highlights of here today is one, the accuracy of your conductivity sensor plays a very important role on the chemical consumption, okay? Phase separation using a turbidity sensor or a color sensor also plays a very important role, especially if you want to reduce the water consumption and increase your your product recovery. And number 3, I think it was really the highlight of the presentation, especially in the last part. We now have a new sensor that is able to measure buildup in process without the need to open or disassemble any other process. Do you want to make any other comments here, Darren, before we go to the questions?
Yeah, so just one thing, we have a very nice tool on our website, Endress.com. We call it Applicator. So if you just search in the search bar Applicator, you'll actually see this process map amongst other process maps in the food and beverage life science industry that can support you with the various measurement points and the value that these measurement points can add to your process.
Excellent. Thank you very much, Darren. I think we can now go to the questions. We have a couple of questions that popped up here. Yeah, you still
can all E&H temperature sensors be calibrated? Yeah, with respect. So the economical sensor that I mentioned, that's a plug and play. Not really. That's honestly a plug and play device, but everything else is fully calibrated or can be.
Excellent. Thank you very much, dear. We do have some other questions here. There's another one related to temperature. Do we have a trust sense for lower temperature?
Not at the moment. So as I mentioned, this took 10 years to develop, the 118-degree sensor. We are currently trialing out the 55-degree. It took us about 3 years of R&D for the 55-degree sensor. So this is being trialed out, and the results are looking promising. So hopefully in the coming months or next year, you should be seeing that we're releasing a self-calibrating probe at 55 degrees.
Excellent. Yeah, just one comment on that. We do have some customers that are using the Trust Sense in the food and beverage industry, but they're using these the Trust Sense, let's say, feature to reduce their calibration time. So whenever they need to do any kind of calibration, they just quickly remove the sensor from the process. They just put it in the thermal bath, it goes up to 118 degrees. Once it reaches 118 degrees, it self-calibrates, and the customer just take it back to the process, so they can reduce the amount of time during calibration as well. Another question, this one is around the QMW43. Does the QMW43 has any hygienic approval? As I already mentioned, yes, it has EH, EVG, and 3H, so you don't need to worry about it. And what we often try to do with the QMW43 is, let's say the best installation condition is to have in a flush mounting position, because the sensor can mimic or can copy the inside of pipes and tanks. So you have the same buildup over the sensor as you would have anywhere else around in that area. And there's another question, maybe Diren or Alu can answer. What are the QMW43 outputs?
So Alu, do you want to answer this?
Yeah, sure. Basically the output of the QMW43, as we mentioned, the buildup heights as well as conductivity, and also they come about as a result of the connections. You can have both analog, which is like 4 to 20, as well as digital in the form of IO-Link, which has actually opened up a lot of possibilities. But the main two outputs are the buildup height and the conductivity, which can be used. However, I should also indicate that the conductivity parts, the conductivity output on the QMW43 is not temperature compensated as it is for our traditional conductivity meters. What do we mean by that? It therefore means that going by the definition of conductivity, an increase in the temperature of the media actually changes the conductivity. It means when you increase the temperature of the media, the conductivity increases. And also when you reduce the temperature of the media, the conductivity reduces. So basically the QMW43 just measures the conductivity of the media at a given temperature.
Excellent. Thank you for the great explanation, Alu. We just have one final question. We'll come back to you later on, Lee. Do you have local support in South Africa? Yes, and one of the presenters will be our contact. Yeah. Right, Diren?
So Lee, just to answer your question, yes, we have a full service team that supports actually sub-equatorial Africa, and we do offer all calibrations, so flow, level, temperature, liquid analysis, everything. Samson, I see you do ask, how often do these sensors get calibrated? I'm not sure what you're referring to by you talking about these sensors, but in terms of calibration intervals, this depends on the process that's running in the plant. You know, as an example, temperature, normally the rule of thumb is once a year that they get calibrated. pH, on the other hand, gets calibrated. Sometimes I've seen once a week, sometimes every month, as an example. So maybe if you want, you can get in touch with me and we can chat about how often a calibration should occur. I do see a hi. Will the micropilot radar shoot through a HDPE 5mm wall thickness tank? Yes, it will. Radars do work through these tanks. We've had many successful trials whereby we don't have to cut a hole in the tank. We actually measure through them. So yeah.
Excellent. Cool. Thank you very much. So I think we're running. Sorry, Alu, you want to say something?
Yes, just on the calibration issue, specifically for the liquid trend QMW43 requires no calibration. You cannot do no calibration on it. It's calibrated before it leaves the factory. So it's just a matter of just installing it and that's it. You don't require to do any calibration.
Excellent. That's a really good point. Cool. All right. So I think we got into the end of today's presentation. So thank you all very much for your interaction, for your attendance. It was a really good. We do have some other questions here, but unfortunately we don't have time to go through all of them. So you're going to receive a follow-up email with the webinar recording, and if you haven't downloaded the presentation, you can still have 1 minute. But thank you very much, and yes, see you next time. Bye, everyone.
Thank you. Bye.
Bye.